Hi, so today I'd like to talk a little bit about Fermi statistics and fermions and Fermi energies. So to get started with that, let's first remind ourselves of spin. So there's three different main classes of particles in statistical mechanics, and those three classes of particles are, fermions, bosons, and then basically classical particles or ideal gas type molecules or particles. And the differences in between these three classes of atoms or molecules, particles, are the spin. So what is spin? Well, spin is the intrinsic angular momentum, which leads to, of course, an intrinsic magnetic moment of a particle. So lots of people have in their heads this idea of a single particle sitting there, and just like the Earth spins on its axis, it spins, right? And that would give something an angular momentum. Of course, this idea really breaks down. It's not truly valid. For all we know, electrons are point particles. We haven't managed to successfully measure a diameter, for example. So as far as we know, it's infinitesimally small. And so how something that's infinitesimally small spins on its axis is a really good question. Nevertheless, this idea helps a lot of folks wrap their head around the fact that particles do have an intrinsic angular momentum to them. Okay? And I think of this these days much like I would think of the charge of a particle or the mass of a particle. Just like that, it also has this other property called spin. All right? So this is the angular momentum. Now, the spin is quantized for quantum particles. Okay? It can't just have any old value. In other words, it's going to have certain discrete values. So that's dictated by the spin quantum number. Now, for fermions, and in that class of particles, an electron is a fermion, the spin is a half integer. So for an electron, for example, the spin quantum number S is 1/2. Now, we often talk about spin up and down, right? And that has to do with how these particles behave in a magnetic field. Okay, so if you have an intrinsic magnetic moment, dictated, of course, by the fact that you have an intrinsic angular momentum, then the particle could either align with that magnetic field or be anti-parallel to the field. Okay, and this corresponds to spin up and spin down particles. And the way that we quantify that is with the magnetic spin quantum number m sub s, whose value for an electron is either plus or minus 1/2. So plus 1/2 corresponds to spin up, minus 1/2 is spin down. So the electron, as I said, is one of many fermions. Fermions have half integer spin. Other fermions that you may have heard of include protons and neutrons, which are also present in atoms. Now, what's special about fermions is that they obey the Pauli exclusion principle. And that means that they are dictated by a set of statistics that are distinct from other types of particles, like bosons or classical particles. So let's remind ourselves what the exclusion principle is. The exclusion principle states that no two fermions that are in the same potential can have the same set of quantum numbers. So what this means for example, electrons in an atom is that no two electrons in the same atom can have the exact same set of quantum numbers. And if this weren't valid, what would happen is that all the electrons, to be in their lowest energy state, would radiate away until they were in the lowest ground state. But that's not what happens, and so that dictates the structure of our periodic table, for example, amongst other things. Now, in this case, I'm not focusing in on what's going on with electrons within an atom. I'm going to talk today about the free electron C, or the free electron gas, that's present for conduction electrons in a metal lattice. Okay, so to talk about this, I'm going to have to talk about the Fermi-Dirac distribution function. And so I thought it might be worthwhile to remind you of what a distribution function is before I do anything else. Okay? So distribution functions is an idea that comes from statistics. So basically, we do a lot of histograms and distribution functions in a lot of different fields. They start off, say, maybe as a histogram here. This is, for example, call center hold time versus number of minutes for a business. Okay, so you can see here lots of different folks like to use histograms and distribution functions. Basically, the idea is that you have, so for example here for call center hold time, it's the number of customers willing to wait versus the number of minutes they're put on hold, right? So how many customers are actually willing to wait 9 to 10 minutes? It's not very much, right? All right, so what's going on with the statistics that we're talking about today is in physics, we're really interested in how particles distribute their energies within a system. So how many particles might have X amount of energy? How many particles might have Y amount of energy? And if you have a big collection of particles and you plot their energies, right, how many particles will you find in a given energy range? And so that's the kind of histogram that we're plotting. Now, when you're looking at large collections of data, what happens is your bins, how wide your bin is there in that bin histogram, gets narrower and narrower, and it starts to look, your function starts to look more and more continuous. So you can see here it's done a little bit in this image. They're plotting out where the top of that bin is for each one, and you can see that it starts to look like a continuous function. And the more data you got, right, the more continuous it would look. So this is a distribution function. So you can think in your head, okay, I've got histograms, and then as it gets more and more data, my bins get smaller and smaller, I've got distribution functions. But they do kind of the same thing. Now, what distribution functions do we have in physics that do these sorts of things? Well, there's three common classes of particles that you learn about in statistical mechanics. Those are your bosons, your fermions, and then your classical particles. And to describe classical particles, you usually think of ideal gases, right? So those are three classes of particles. And so how are the energy states for a bunch of these types of particles? How are they distributed, right? How does it go for classes of particles with different temperature ranges? All right. So to do that, we have three classes of statistics: Fermi-Dirac statistics, Maxwell-Boltzmann statistics, those describe classical particles, and Bose-Einstein statistics, and those describe bosons. Now, we're not going to talk about Maxwell-Boltzmann or Bose-Einstein today. I'm going to focus in on Fermi-Dirac because those describe fermions, right? And that's what we're interested in for the conduction electrons. So, what is the distribution function for fermions? What is the Fermi-Dirac distribution function? Here it is shown. The function that I'm showing here is f of epsilon. Here, epsilon represents the energy that a particle might have. F of epsilon is equal to 1 over e to the minus epsilon minus the Fermi energy divided by kT plus 1. Now here, K is Boltzmann's constant, which in SI units is 1.381 times 10 to the minus 23 joules per Kelvin, right? Epsilon sub F is the Fermi energy. And we're going to be talking about a lot about the Fermi energy here in a second. And of course, T is the temperature, okay? Now, the Fermi energy is a very important energy when describing fermions, all right? What it is in a nutshell, and we'll talk about this more, is the maximum possible energy that a particle can have when that system of fermions is at absolute zero, okay? So that's the highest occupied energy state at absolute zero for a system of fermions. Okay, now, how does this function describe that? Let's get into this, okay? So, if you have a particle energy is equal to the Fermi energy, and then you solve for what that's like here in this Fermi-Dirac distribution function f of epsilon, then what would happen is in the e to the epsilon minus Fermi energy over kT term, e would equal e Fermi, and then you'd have e to the 0 there in the bottom. E to the 0 is 1. So then you would have 1 over 1 plus 1, which is 1/2. So if the particle's energy equals the Fermi energy, then that value of your Fermi-Dirac distribution function is 1/2, and that's true no matter the temperature, all right? So that's always true. Now, what happens as you take T to 0, right? What happens is you shrink that temperature down towards 0, okay? Well, we've got two possibilities. First of all, if you're looking at a particle whose energy is greater than the Fermi energy, then you've got, over here, 1 over something, e to the something, divided by 0, right? So basically, your term in your exponential there, it goes to infinity. So you have 1 over e to the infinity plus 1, right? That goes to 1 over infinity, which is 0, all right? So if your particle's energy is greater than the Fermi energy, as t approaches 0, your Fermi-Dirac distribution function equals 0. All right, what does that mean? Well, this is how the energies of the particles are distributed, right? That's what the distribution function describes. if F goes to 0 as T goes to 0, then that means there aren't any particles in that energy state, which means that if the energy is greater than the Fermi energy as T approaches 0, then that's an unoccupied state, right? You're not going to get particles that have an energy greater than the Fermi energy as T approaches 0. All right, let's look at what happens if the energy epsilon is less than the Fermi energy as T approaches 0, okay? In that case, epsilon minus E Fermi, right, the Fermi energy, would be a negative number, right? In that case, you have e to the negative number divided by 0. So that means that it approaches negative infinity, right? So then you have 1 over e to the minus infinity plus 1. Well, e to the minus infinity is 0, right? So that means that you have 1 over 1, which is 1. So basically, if the energy of the particle is less than the Fermi energy as T approaches 0, then that's definitely an occupied state, right? It's occupied with a probability of 100%, 1. So what this means is that if you have 0 Kelvin, right, fermions are going to occupy the lowest possible energy states available to them. As they chill down, cool off, they're going to be in the lowest possible state that they can get. At near 0 Kelvin, there's little chance that you're going to have thermal agitation kicking a fermion up to an energy greater than the Fermi energy, right? So that means that the probability that a fermion will have an energy greater than the Fermi energy at 0 Kelvin is 0, right? So you can consider the Fermi energy to be the highest energy state available to fermions at low temperatures. So what does the Fermi-Dirac distribution function look like? Well, if you're at 0 Kelvin, it looks like a step function, okay? So here you have this step function in blue, and the cutoff is the Fermi energy here at T is equal to 0. So basically, the Fermi-Dirac distribution function is 1 for energies less than the Fermi energy, and it's 0 if it's greater than the Fermi energy. Okay, now, what happens if the temperature is greater than 0? Well, what happens is it gets rounded off from the step function. So you have sort of a rounded off step for T greater than 0. Now, as we said, if the energy is equal to the Fermi energy, then the distribution there is 1/2 no matter the temperature. So you can see that right here, this blue line, right, which represents the distribution function for a greater temperature, intersects the dashed box line, right? And where does it intersect it? At 1/2. Okay, so that's always going to be the case. But it gets rounded off, and what that means is that if you're above the Fermi energy, right, for T greater than 0, there's a chance that you'll have higher energy states occupied, right? So as it heats up, you can have energies greater than the Fermi energy, and as it heats up more, you'll get more there, all right? If it gets really large, then it's going to look like a simple decaying exponential. But I've got to tell you that this happens at really, really high temperatures, and you're probably going to have phase transitions of your material before your distribution function looks like that. So at reasonable temperatures, this rounded off distribution function is more along the lines of what we're thinking. Okay, so how do we find an expression for the Fermi energy? Well, we're going to model the conduction electrons in a metal as a free electron gas. So what we're going to do is we're going to confine them to the volume of the metal. So you can think of them as being in a box, right? An infinite square well, 3 dimensions, right? And it's trapped. They're trapped in that box. So in that well, the total energy of the electrons is going to be the kinetic energy, because remember, for our infinite square well potential, we model the potential as infinite outside of the well, but inside the well, we model it as 0. So this is, you should think of your quantum square well right here. So basically, remember in a previous lecture, we covered what the energy states were for a particle confined to an infinite square well in 3 dimensions. And that's described by this function here. The energy is equal to h squared over 8 times m times l squared times the sum of the squares of the quantum numbers in each dimension, which is nx squared plus ny squared plus nz squared. Now here, h is Planck's constant, which is 6.626 times 10 to the minus 34 in SI units. The m is the mass of the particle that's confined. So here that would be the mass of an electron, which is 9.11 times 10 to the minus 31 kilograms. And then L is the length of the well, right? So it's how long the well is in that one direction. We're assuming here that it's a cube, basically, so it's confined, and it's got L on all sides. Now, this is the energy, and inside of the well, it's going to be all equal to the kinetic energy. Kinetic energy, remember, can be written as p squared over 2m, where p is the momentum of the particle. Okay, so three-dimensional infinite square well. Now remember that these quantum numbers for the 3D square well are positive integers only. They start at 1 and go up in integer steps from there. So the energy can't be negative, all right? Now, these are also fermions, and they obey the exclusion principle. So what that means is that the energy levels are going to begin at the lowest values of the quantum numbers, and then they're going to fill those states until the maximum possible quantum number is reached. So if we consider the system to be at absolute zero, then the maximum possible quantum numbers are going to combine to give that Fermi energy, right? So here we're merging these two models. So basically, we can say that the Fermi energy is going to equal to h squared times what we are calling n max squared divided by 8nl squared. Now here, n max squared is going to be the squares, the sum of the squares of the quantum numbers for each direction. So n max squared is equal to nx squared plus ny squared plus nz squared. Okay? Now what would that look like? Well, you've got only positive numbers. So if you wanted to plot this out, what it might look like in quantum number space, then you would have your x, y, and z quantum numbers all plotted on each independent perpendicular axis. So this is quantum number space plot of it right here with nx, ny, and nz. In max, you could think of like the radius of this little section of a sphere, if you'd like, okay? Now, the value of n max is going to depend on the total number of conduction electrons that you have, which I'll call big N, okay? Remember that there can be two fermions, one spin up and one spin down, for each independent distinct set of nx, ny, and nz. And that's because of the, Pauli exclusion principle. So you have these energy states. They're going to be really close together, right? Because you've got so many conduction electrons that these energy states are going to look really close together. So we're going to assume that they start to look continuous. Now this model does break down, and I'm going to talk about that later. But for now, let's go with it, okay? So they're going to seem continuous in a bulk solid. So we can find the number of states by finding the volume of that 1/8 of a sphere that we've got here in our plot as they make up in quantum number space. And then we're going to multiply that volume of that sphere in quantum number space by 2 to account for the spin up and the spin down particles, okay? So here, big N is 2 times the volume of my little 1/8 sphere here. So you've got 1/8 of a sphere, so the volume of a sphere, of course, is 4/3 pi r cubed, right? So we have 1/8 times 4/3 times pi times n max cubed. Remember, we think of n max like we think of the radius of our little 1/8 sphere. And then we multiply that by 2, because we've got a spin up and a spin down for each quantum state. So that gives us big N is equal to 2 times 1/8 times 4/3 times pi n max cubed. Okay, so how am I going to get a Fermi energy out of this? Right, all right, here we go. The number of conduction electrons, if I simplify this previous expression here, I have n times 2 times 1/8 times 4/3 times pi n max cubed. Right, we get some cancellation there. So the 8 cancels out with the 2 and the 4 on top, and I end up with big N is equal to pi n max cubed over 3. Now I can solve for n max, right, using this equation. N max would be 3 times big N over pi to the 1/3 power, right, taking the cube root there. Now I'm going to plug that equation in, right, plugging in for n max into our equation for the Fermi energy. We said that the Fermi energy should be proportional to this infinite square well energy, which we said was h squared times n max squared over 8ml squared, right? So if I plug in for n max, I've got the n max is equal to 3 over pi to the 1/3 power, right? And then I have this L squared on the bottom here. So I have an n max squared over L squared. So if I pull both of those inside this 1/3 root bit here, then what I end up with after a little bit of algebra, you can pause it here if you need to think about the algebra. That's h squared over 8n times 3n over pi v to the 2/3 power. Now remember, what's the v? V is volume, and the volume of our 3D box, since it's a cube with sides L, would be L cubed. And see here, if I take 1 over L cubed to the 2/3 power, I get L squared. Okay. All right, so that was our equation for the Fermi energy. All right, the Fermi energy was h squared over 8m times 3n over pi v to the 2/3 power. Okay, you can see there that it's mostly dependent upon n over v, which is the number of conduction electrons per unit volume. And that's going to vary from material to material. So this is a material property, okay? So what is this Fermi energy? It's the energy that conduction electrons in the highest energy levels have at 0 Kelvin. Now here's another fun thing. Students often have the misconception that cold means slow. And this comes from the ideal gas model, right? We say that in the ideal gas you have these atoms that are zipping around, right, at high speeds, and then as you chill it down they get slower and slower. So that's the conception there. But not all particles are classical particles, are they? So these fermions aren't. They're not classical particles. They follow a different set of statistics. So we can find how fast they're going, or at least a ballpark estimate of how fast they're going, by finding what's called the Fermi speed. So we can set the Fermi energy, which we have an equation for, equal to a kinetic energy, and say that that's 1/2 mv Fermi squared, right? And then we can solve for v Fermi and find out a ballpark estimate about how fast they're going. So let's do an example problem of all this and kind of cement it in our heads. Silver donates 1 conduction electron per atom. So we're going to use the density of silver, which is given as 1.05 times 10 to the 4th kilograms per cubic meter, and the molar mass of silver, which is 107.87 grams per mole, to find the density of conduction electrons in silver. And then we're going to use that to calculate the Fermi energy of silver and the Fermi speed of silver. So how do we do that? Well, you start off at a density, and you basically just do a unit conversion. So silver has a density of 1.05 times 10 to the 4th kilograms per cubic meter, all right? Now I'm going to go ahead and use that molar mass. So I'm going to convert from kilograms to grams. 1 kilogram has 1,000 grams, right? And then I'm going to use the molar mass of silver. So 1 mole is 107.87 grams. So I multiply by 1,000, I divide by 107.87, then I have the number of moles of silver per cubic meter. But I don't want moles of silver, I want number of conduction electrons. So first, I'm going to convert to the number of atoms per cubic meter, right? 6.022 times 10 to the 23rd atoms per mole. And when I do that, I end up with a density of 5.86 times 10 to the 28th silver atoms per cubic meter. Well, each silver atom contributes 1 conduction electron. So that means that the density of conduction electrons is actually 5.86 times 10 to the 28th conduction electrons per cubic meter. Now, that is going to be N over V, big N over V, right? And that goes into our formula for our Fermi energy. The rest of our Fermi energy formula is just fundamental constants. We've got H, which is Planck's constant, and we've got the mass of the conduction electron, which is 9.11 times 10 to the minus 31 kilograms. So, plugging all that into our calculators, right, we end up with a Fermi energy of 8.8 times 10 to the minus 19 joules. Doing a conversion from joules to electron volts, which is a more convenient unit, quite frankly, for a Fermi energy, we end up with 5.5 electron volts for the Fermi energy of silver. Now that we have the Fermi energy, right, we can use that to find the Fermi speed. You set the Fermi energy equal to 1/2 mv Fermi squared, right? So you can find the Fermi speed by taking the square root of 2 times the Fermi energy divided by the mass. Doing that here, I see that the Fermi speed of silver is 1.4 times 10 to the 6th meters per second. So that's not slow, right? That's like 0.3% of the speed of light. So it's going pretty fast, even at very low temperatures. Now, what does this all mean in terms of what we learned before about band gaps? Okay, so let's think about the band gap model and contrast that to this Fermi-Dirac statistical model for just a second. And so here I want to tell you this. Fermi-Dirac statistics are wonderful, but you have to bear in mind it's only a model, and what are the limitations of that model? So the Fermi-Dirac function is a continuous function. Now, it's attempting to model something that's discretized, but it makes a big assumption there, and it says that we're going to assume that the energy states are close enough together that they look continuous. And that was an assumption that we made way back at the beginning, and that's not actually true, okay? We know from our band gap model that we discussed in a previous lecture that there's actually allowed bands of energy states, and that in between those allowed bands of energy states, there's gaps, band gaps, right? So if you were to take the Fermi energy kind of model and map it over onto the band gap model, this is more like what you would see up here in the top portion of this figure as the temperature approaches 0 Kelvin. Remember that what we said was that 0 Kelvin is the maximum possible allowed energy state, right? That's max possible. What would that mean to take it over into our band gap model? Well, what it would mean is that for conductors, it would lie kind of in the middle here of this valence band and the conduction band. And you can see that at 0 Kelvin, there's not a lot of electrons in the conduction band, but there are still some. And as you promote more and more as it gets hotter and hotter, you're going to fill that conduction band more and more. But for a metal, even at 0 Kelvin, you've got some electrons that are in that conduction band. And so you can see here, this dashed line right here represents the Fermi energy, and you can see that you've got this kind of purple region here where you've got some electrons that are in that conduction band. Now, for semiconductors, what happens is that there's a band gap in between the valence band and the conduction band. And for semiconductors, the Fermi energy lies in the gap in between the valence band and the conduction band. So that means that semiconductors really don't have anything as at 0 Kelvin that is above the Fermi energy. And there really is that gap there, okay? And all the ones underneath are occupied states. Then you have this gap in between the valence and the conduction band. The Fermi energy is there in the middle. So between the Fermi energy and the top of the valence band, there's actually no electrons occupying that state, unlike in the conduction band where you really do have some, right? Now, in an insulator, you've got a huge gap in between the valence band and the conduction band. The Fermi energy lies in the middle there, but there's actually a decent amount of energy in between the top of where the electrons really are in this valence band and the Fermi energy that's seen, okay? Now, what happens as the temperature increases? Now we're looking here at the bottom of the plot. The Fermi-Dirac statistic says that this distribution function gets rounded out, and you actually have some electrons that are above the Fermi energy as you increase the temperature, right? Okay, well, what does that look like? Well, what we know for real is that we have this Fermi energy right here, and it's in the middle, say, for semiconductors. It's in the middle between the valence and the conduction band, right there in the band gap there. And then what happens is, as the temperature increases, you get, in a semiconductor, more electrons promoted from the valence to the conduction band. And so they're promoted to above the Fermi energy when they jump that band gap, okay? So the models are different, and they assume different things, right? But you can see how they come together here. Well, I hope you enjoyed that. If you have any lingering questions, let me know, and I'll see you in class.